My greetings to everyone. My name is Olga Avsajanishvili. I am a researcher from the Evgeny Georgian National Astrophysical Observatory. My areas of research in cosmology are study of cosmological models beyond the standard scenario, inflation, and the large-scale structure of the universe. I'd like to present to you my talk, Cosmological, Mass Varying Neutrino Model. In 1998, two teams under the leading of Permuta and Rees, studying distance type 1a supernova, independently discovered that our universe is expanding with an acceleration. There are two opposite approaches for the explanation of this phenomenon: modification of the general theory of relativity on large scales and the existence of dark energy or dark barotropic fluid with negative pressure. There are numerous dark energy models, and a partial list of which is presented here. The simplest description for dark energy is the concept of vacuum energy, or the time-independent cosmological constant lambda, first introduced by Albert Einstein. The cosmological model based on such a description of dark energy in the special flat universe is called the standard concordance or the fiducial lambda-cold dark matter model. This model is based on the general theory of relativity for description of gravity in the universe on large scales. Based on the ΛCDM model, about 95% of the total energy density in the universe in the dark invisible form with unknown nature, dark energy and dark matter. Dark matter manifests itself in the abnormally high velocity of rotation of the outer regions of galaxies, wherein dark matter particles weakly interact with an electromagnetic radiation and only gravitationally interact with an ordinary matter. Being still a fiducial cosmological model at present, the ΛCDM model has several still unresolved problems, the number of which increases as more accurate observational data are obtained. The main of which are the fine-tuning or cosmological constant problem, the coincidence problem, the Hubble parameter tension problem, the parameter SA tension problem, the problem of the shape of the universe, to be precise, the preference for observational data of the closed hyperspaces, and preference for observational data of dynamical dark energy. One of the alternatives to the ΛCDM model are dynamical scalar field ϕCDM models. In these models, dark energy is represented in the form of the slowly varying uniform cosmological scalar field at present. This family of models avoids the coincidence problem of the ΛCDM model. In these models, the energy density and pressure are time-dependent functions under the assumption that the scalar field is described by the ideal barotropic fluid model. In general, dark energy models are characterized by the equation of state parameter, which is the ratio of pressure and energy density. If for the ΛCDM model, the equation of state parameter is a constant and equals -1, then for ϕCDM models, the equation of state parameter is a time-dependent function. Dynamical dark energy can mimic the cosmological constant at present, while becoming almost indistinguishable from it. Mass varying neutrino model can explain the origin of the neutrino mass. Moreover, this model can resolve the coincidence problem of the ΛCDM model, that is, mass varying neutrino model answers to the question, why do dark matter, here neutrinos, and dark energy have comparable energy scales today, despite having evolved differently? From the essence of the coincidence problem, it follows that dark matter and dark energy interacted with each other during their evolution. It can also be assumed that dark matter particles had a mass that changed over time. Further, Nelson and Weiner elaborated the mechanism of the varying mass particles and applied it to neutrinos. As a result, a mass varying neutrino model was created. In mass varying neutrino model, the fermionic field interacts with the scalar field via the Yukawa coupling. In this model, the fermionic mass is generated due to violation of the chiral symmetry in the direct sector of the Lagrangian, the value of which subsequently changes with time. The total thermodynamic potential of the coupled fermionic and scalar fields can be found in the saddle point approximation, minimizing the path integral. The saddle point approximation coincides with the condition of minimum of the total thermodynamic potential at equilibrium for the fixed temperature and chemical potential values. As a consequence, neutrinos acquire mass at the critical point. We studied the interaction of the fermionic field and the scalar field with inverse power law, a Ratra-Peebles potential, which doesn't have a non-trivial minimum. Here, alpha and m are positive model parameters. Parameter alpha defines the steepness of the potential. For alpha equals 0, the phi CDM model reduces to the lambda CDM model. They have minimized the total potential and solved the mass equation expressed through the dimensionless variables. In the result, they have defined the values of the scale factor and the neutrino mass at the critical point depending on the alpha parameter. Before interaction with the scalar field, neutrinos are in this free-streaming regime. Their masses are relativistic. After the critical point, neutrinos become non-relativistic, and a neutrino non-energy dark energy fluid is formed. To study the evolution of this fluid, they jointly integrated the first Friedman and scalar fluid equations. They fixed the value of the current matter density parameter and considered the total effective potential consisting of the Ratra-Peebles potential and the additional component connected to neutrino. In the result, they found that with increase in the value of the model parameter alpha, the value of the scale factor at the critical point decreases. That is, the moment of the neutrino non-relativization occurs early. The value of the mass scale for the scalar field increases too. With an increase in the value of the model parameter alpha, the value of the initial neutrino mass and accordingly the value of the neutrino mass increases for all scale factors up to the present epoch. Then the value of the alpha parameter changes. The mass of the scalar field develops differently in difference dependent on the scale factor. Moreover, all these tracks converge to a zero mass value in the present epoch. That is, they have an attractor solution in this point. By studying the mutual influence of the neutrino mass and the scalar field potential, they found that with an increase in the value of the model parameter alpha, the value of the scalar field potential increases too. It happens because the scalar field potential is determined in a specific range of neutrino masses, which depends on the value of the alpha parameter. They also investigated the influence of neutrino dark energy fluid on the expansion rate of the universe. The expansion of the universe occurs more rapidly with increasing the value of the parameter alpha and vice versa. They studied the dependence of the dimensionless density of the thermodynamic potential on the value of the alpha parameter at a fixed critical temperature. With an increase in the value of the model parameter alpha, the moment of the neutrino non-relativization occurs earlier. Therefore, the temperature at the critical point is higher. As a result, the negative contribution of the density of the thermodynamic potential for neutrinos increases, while it increases faster than the contribution of the density of the thermodynamic potential for the scalar field, which leads to a decrease in the value of the total density to the thermodynamic potential. In this figure, clearly distinguishable areas can be identified. The area of minimum potential or the area of neutrino oscillation, as well as the area of an unstable maximum, after which the total density of the thermodynamic potential rolls down to its minimum. And I'd like to conclude that studying the interaction of the fermionic field and the scalar field with the Ratra-Peebles potential, we found that with increasing the value of the parameter alpha, that is, with strengthening of the scalar field, the moment of the neutrino's non-relativization occurs earlier, the temperature at the critical point increases, the value of the initial neutrino mass and accordingly the value of the neutrino mass increases for all scale factors up to the present epoch. The expansion of the universe occurs faster, and the value of the total density of the thermodynamic potential decreases. With a change in the value of the model parameter alpha, the mass of the scalar field develops differently in the dependence on the scale factor. But all these tracks converge to a zero mass value in the present epoch. That is, they have an attractor solution in this point. Thank you for your kind attention.